Hello friends, welcome to CEC live lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor of Computer Science at Jesus and Mary College, University of Delhi. So friends, in the previous lecture of this series, we were talking about the problem of fragmentation and how memory allocation leads to internal and external fragmentation. So we had seen that basically what is fragmentation, that when the total memory available is enough for hosting a process or holding a process, but that memory has been divided into, or it has been broken down into fragments or individual blocks, and none of the blocks is able to hold a process. So in totality memory is available, but still it cannot be allocated because the size is not enough for a process to hold in individual holes. Now what are the solutions to this problem, right? Whether it is external or internal, what are the solutions? So first let us look at the problem of external fragmentation and how it can be solved. So external fragmentation, the fragments are created in the entire system memory, and therefore one solution which is suggested is known as compaction, right? So what is compaction? Basically in compaction the memory will be shuffled, the contents of the memory will be shuffled and all the free memory will be placed together in one large block, and the occupied or the allocated memory will be put in another block, right? Although this sounds very fascinating, but it is not always so easily possible. It is not a very feasible approach. Why? Because if it is, if the relocation is static, right, then it is done at the assembly or the load time of the process. So then compaction cannot be done. It is only possible, compaction is only possible when we have a dynamic relocation, right? That is, we are going to load it at the execution time. We are going to do this compaction at the execution time. So if addresses, they are relocated dynamically, then relocation requires only moving the program and data and then changing the base register to reflect the new base address, right? So you are shifting the entire program and data to a new address. Now if it is dynamic, then you only have to change the base address. The rest of the thing will be calculated dynamically, right? So when compaction is possible, and we have to also understand that there is a cost to it, right? It is a process which is an expensive process. This compaction scheme is an expensive scheme, right? Why do we say that compaction is an expensive scheme? Because the simplest compaction algorithm, which is to move all processes towards one end of the memory and all holes towards another direction, it will produce one large hole of available memory. But this relocation will have its own overheads. Moving all processes and moving all holes and then relocating them will have its own cost. It will have its own overheads. Therefore it is called an expensive approach. So another possible solution other than compaction for the external fragmentation problem is to permit the logical address space of the process to be non-contiguous. Non-contiguous means that we do not need contiguous memory for a particular process. We can store different parts of the process in different places within the memory. So a process will be allocated physical memory wherever such memory is available. It will not look for larger chunk. It is non-contiguous basically. So for this approach there are two complementary schemes. There are two complementary techniques which are used for this kind of solution, and these are very important and very, very practical approaches, and they have a lot of importance in case of research also, and a lot of research is being done in this case because a lot of improvisation is still possible in these areas. So the two techniques which will be used for again it is for addressing the problem of fragmentation, external fragmentation. The first approach is called segmentation and the second approach is called paging, right? And we can also combine these two approaches, that is segmentation and paging are two separate techniques, but these are also used as a combination in some of the system, right? Because fragmentation is a very general problem, right, and it can occur wherever we have to manage blocks of data. So therefore this problem needs to be accessed. So first we will look at the first technique, which is segmentation, and how we can use segmentation to overcome the problem of fragmentation, right? So we've already understand one thing, that the user's view of the memory is very different from the actual physical memory, and the programmer's view of the memory is also quite different from the actual physical memory, right? So therefore to deal with the memory in terms of its physical properties is very inconvenient to both the operating system and the programming. How actually the memory is organized, how the physical properties of the memory is laid down, it is not easy for the operating system nor for the programmer to understand that kind of a structure. So what are we aiming at? We are aiming that there is hardware which will provide a mechanism that you can map the programmer's view to the actual physical memory. So we are trying to devise a system so that this mapping can take place, right? So the system would have more freedom to manage the memory, and while the programmer would have a natural programming environment. So segmentation is the technique, is the tool in which this kind of a mechanism can be developed, this kind of a mechanism can be created, right? So what are we going to do here? We are going to create a similarity, we are going to create a mapping between the physical memory and the programmer's view of the memory, or the say logical memory, right? So we know that programmers, they view memory as a collection of variable sized segments, right, with no necessary ordering among the segments, right. So as a programmer, when we are looking at memory, we know that there are small chunks of memory and we don't even bother to know how these are organized. So when a person is writing a program, or when a programmer is designing, then how in case of say modular programming, how it is done? It is generally that there is one main program, and that main program will have some methods, it will have some procedures, it will have some functions, right. Then it will also have some data structures, it will have some objects, arrays, stacks, variable and so on, right. So these are all the parts of the program which the programmer wants to put, or which the programmer wants to put it on the memory. Now each of these modules, whether it is a function or it is a procedure or it is the data element, right. So whether it is a variable or it is a stack or whatever, they all are referred to by a name, right. So the programmer talks about the stack or the math library and the main programmer without caring about where these are residing in the memory. What is the address in the memory these elements occupy? They are not bothered. They because they have a name, they will access that data with a name. For example, they have created a variable number 1. So they will access that variable using that variable name. They will not bother to know where it is exactly going to save, right. It's not their concern, right. So whether it is stored before the one function or it is stored after a function, it doesn't matter. And also the segments, they will vary in length, and the length of each is intrinsically defined by its purpose in the program, right. We all know that the segments are created and their length is decided, right. So elements within a segment are identified by their offset from the beginning of the segment, right. So the first statement of the program say we say the first statement of the program, or we say the 7th frame entry in the stack, or we say the 5th instruction of a particular function, or so on. So we have a starting point of the segment, and from that we calculate the offset. So 5th instruction in a function means that there is a first instruction, we know the starting point, and counting from the first instruction we are going to the 5th instruction. So we can we can find out the element, right. So this picture actually shows that how the programmer views the program, how the programmer visualizes the program. So they have created these separate logical addresses. So there is one for main program, there is one for library, there is one for stack, there is one for SQRT. SQRT is nothing, any function basically. So basically they are, these are the segments, and the entire thing is the memory. So how a programmer is looking at it is actually very different from how the memory is actually laid out, right. So segmentation is basically a memory management scheme which supports the programmer's view of the memory, right. So a logical address space is a collection of segments, right. So these are segments, means these are different parts, and every segment will have a name and it will have a length, right. So the addresses specify both the segment name and the offset within the segment. So we will know that there are two quantities which the programmer will have to specify, right. So first property or the first quantity will be the segment name, and the second quantity will be the offset which the programmer has to specify, right. So for simplicity of implementation, segments will be numbered because names are difficult. So the segments are also numbered, and they are referred to by a segment number instead of name, and the logical address therefore will have two tuples or two fields basically. One will be the segment number and the second will be the offset, right. So the programmer has to access anything using these two quantities, right. So normally if we look at a C program, when a program is compiled, so what happens, the compiler automatically constructs the segments which are reflecting the input program. So if it is a C compiler, so it will create separate segments. For example, it will create one segment for the code, it will create another segment for global variables, it will create another segment from the for the memory, or the heap from which the memory will be allocated for the program, then the stacks which are used in by the threads, and the standard C library. So all these segments will be created by the compiler at the execution time or when the program is being compiled. Libraries which are linked in during compile time, they may also be assigned separate segments. So the loader would take all these segments and assign them segment number. So basically the idea is that the program, when it is compiled, the compiler will identify the segments, and the loader is going to assign the numbers to each of the segments, right. So this is how segmentation works. But segmentation also, it solves the problems partially, and therefore another technique is also very commonly used, and it's also very crucial, which is known as the paging technique, right. So segmentation is actually allowing the physical address space of a process to be non-contiguous. That is, the process can use spaces in the physical memory which are not continuous. Paging is another scheme of memory management which offers this kind of advantage, right. However, paging avoids external fragmentation and the need for compaction, whereas segmentation does not, right. So even when you are doing segmentation, there is a problem of this issue of external fragmentation, somewhere it remains, and there is also a need for compaction that we already discussed. Right. So it also solves the considerable problem of fitting memory chunks of varying sizes onto the backing store. Backing store means the secondary storage where we are talking, because the problem of fragmentation, if you understand, it is not just a problem of the memory, but it is also a problem of the secondary storage, or say the magnetic disk, because there also this kind of fragments will be created, and there the problem is further aggravated because the speed of the secondary storage is also very slow. Right. So, most important memory management scheme which is used is called introduction of paging. Right. So, the problem is that the code fragments or the data residing in the main memory, it has to be swapped out and space has to be found on the backing store. Right. So, the same thing which I just discussed, that compaction is also impossible in the backing store, right, because we already discussed of the issues which came with compaction, right. So, therefore, what is the solution? Paging and different forms of paging is used in most operating system, right, even in case of mainframe operating systems and even in case of smartphones, paging is used. Now, how is paging implemented? In paging, basically there is a very close cooperation between the operating system and the computer hardware. Both these two components, the operating system and the hardware, they work together to implement this scheme of paging. So, first let us understand what is paging and how it is implemented. Right. So, what we are saying is, we are going to talk about two terms. One is called the page and the second is called the frame, right. So, the entire physical memory of the system is divided into fixed size blocks which are known as frames, right. So, the physical memory is divided into blocks, and these blocks are of fixed size and they are known as frames, and the logical memory is broken or it is divided into blocks of the same size, and this is known as pages. Right. So, it is very important that frame refers to blocks of physical memory and page refers to block of logical memory, and the size of the page will match the size of the frame. Right. Now, whenever a process is to be executed, its pages are loaded into any available frames from their source. Right. Now, the source could be a file system or it could be a backing store, it could be anywhere. Right. So, the process, the pages are loaded into the frame. Okay. Now, the backing store is also divided into fixed size blocks and they are the same size as the memory frame or clusters of multiple frames. So, you understand their logical memory is in pages, the main memory has frames, and even the secondary memory has got the frames, and the size of all these three, that is the frames of the memory, the frames of the backing store and the pages of the logical memory is the same, right. So, if more memory is needed, clusters can be formed, right. So, this is very simple idea which we have created, but this can have wider ramifications. For example, we can have a logical address space now which is totally separate from the physical address space, right. So, if a process can have a logical, that is a 64-bit address space, even though the system has got less than 2 raised to the power 64 bytes of physical memory. So, even if the physical memory is less, you can still have a larger logical address space. Right. Now, every address which is generated by the CPU will be divided, actually it is divided into two parts. First is the page number and second is the page offset. We all know that logical address is the address which is generated by the CPU, right. So, it will have two parts, the page number and the page offset. The page number is used as an index into a page table, right. Now, this is very important, that is, what is a page table? A page table basically contains the base address of each page in the physical memory. Base address means where the particular page is stored in the physical memory. Now, this base address is combined with the page offset to define the physical memory address that is sent to the memory unit. Okay. So we have a base address, okay, in the page table, okay, and the base address corresponds to the address in the physical memory, right. So if you look at this diagram, it's very clear that the CPU, you know, it generates a logical address which has got two parts. The part P means the page number and part D means the logical address, or it means the offset, right. The page table basically, it contains the page number and it has the address of the particular page in the physical memory. So there is a mapping, you know, which the page table is doing between the logical address and the physical address, right. So the page number, when it is looked for in the page table, it will give the starting value of the page in the physical memory. So the page table will have that address, and then when this starting address is combined with the offset, it will give the physical address of that particular you know, page in the physical memory, of that particular data or that particular thing in the physical memory, right. So basically paging model is, you know, very important because it is sort of mapping the logical and physical memory space. So if we look here in the logical memory, we have page 0, 1, 2, 3, 4, we have these 4 pages, and in the page table corresponding to each of the page numbers, that is page 0 at, you know, the page number 0 is at fragment number, is at position number 1, right. So it is in the page table, you are having a corresponding location of that particular page in the physical memory. So if we can see here that page number 3 is actually will be found at location number 7 or frame number 7 of the physical memory. So the physical memory is identifying the frame numbers, the page table is having a mapping between the page number and the physical memory or the frame number, and then you have the logical memory. So the page size is also defined by the hardware. Like we have the frame size, page size will also be defined by the hardware. The size of a page is actually a power of 2. So it can vary between 512 bytes and 1 GB per page depending on the computer architecture. Now it's also very important that, you know, a power of 2 is used as a page size because it makes the translation of a logical address into a page number and then a page offset particularly easy, right. So if the size of the logical address space is 2 raised to the power m, say for example, and a page size is 2 raised to the power n bytes, okay, then the high order m minus n bits of a logical address will designate the page number and the n low order bits will designate the offset, right. So therefore we will get the logical address in the form of page number and page offset, right. Now when we use a paging scheme, we have no external fragmentation, right, because any free frame can be allocated to a process that needs it. However, we may have some internal fragmentation, okay. So because frames are allocated as units, right. Now if the memory requirement of a process does not happen to coincide with the page boundaries, okay, then the last frame allocated may not be completely full, right. For example, let's take an example. If the page size is say 2048 bytes, okay, and there is a process which requires say 72,766 bytes. So what will happen? It will use 35 pages plus some extra bytes, right. So it will require 36 frames, right. Now the first 35 frames will be completely occupied, but the last frame may be less occupied. It may be less occupied, and the worst situation can be when there will be one frame which has got only few bytes, say 1 bytes or 2 bytes, right. So therefore that can lead to internal fragmentation and resulting into a loss of one complete frame. But there is the idea is that paging makes the thing absolutely free of external fragmentation any, okay. So if the process size, if you keep it independent of the page size, then we expect that internal fragmentation to average 1/2 page per process, right. So even then, you know, what we say that if you have small page size, that is desirable. This consideration will suggest that okay, keep the small sizes of pages so that you will use lesser frames, you will, you know, you will waste lesser frame. But this is not true, because for each entry in the page table there is an overhead. So if you have too many pages, because if you make smaller page sizes, then you will have too many pages, so then there will be too many entries, right, and therefore that overhead will increase. Also, when you know you have to bring in information, or there is an IO which is happening with the disk, that also is, you know, more efficient when you have more amount of data, that is the size of the transfer is, you know, larger. So that kind of system becomes more efficient. So therefore this is established that larger the page size, the better it will be, and therefore the page sizes have grown over the time, because you know now the size of the processes, the data sets, and even the main memory are growing faster, right. So therefore from 4 KB to 8 KB in the size, the pages are growing, right. And there are some CPU which will support even multiple page sizes. So therefore, you know, there are multiple research which are going on in this area to develop support for on the fly page sizes. That is, the operating system can dynamically decide what is the page size to be used, right. So when a process arrives in the system, its size expressed in pages is examined, and each page of the process needs one frame. So if the process requires n pages, then at least n frames must be available in the memory. If n frames are available, they are allocated to the arriving process. Otherwise, the first page of the process is loaded, okay, and one of the allocated frames, and the frame number is put in the page table for this process. Next page is then loaded into the another frame, and its frame number is also put in the page table, and so on. So this way, you know, the process of paging will work. So we have seen that, you know, paging is an excellent strategy for overcoming external fragmentation, and if you know the correct page size is designed, or the correct page size can be determined, then to a great extent it can also be used for preventing internal fragmentation. So friends, this will be all for today. We will be continuing with some other interesting topic in the next lecture. Till then, thank you.